Everyone, please sign in on the sign-in sheet. Because I know not everyone has, but there's not enough names there. Um. Why are you not working? Oh, there we go. Let me get my microphone out as far as it'll go. Okay. So today we're starting the lecture on chapter 2. This lecture will also include a little bit of chapter 3, but the questions are all from chapter 2. The first few sections of chapter 3 will also be covered because they fit nicely together as part of the history stuff. The worksheet is just the chapter 2 worksheet. There's not a separate chapter 3 worksheet. Yeah, and please sign in on the sheet up front for attendance. So let's start with discussion of the celestial sphere. So the celestial sphere is a way of imaging the sky. It's a tool that we use to talk about where stars are when we look up at the sky. So it's a geocentric, Earth-centered model where if you look up at the sky from Earth, let me just quickly check both. Stars, planets, and other astronomical objects appear to be positioned on a sphere. It's as if we're in the middle of a big ball, and we can look up and see these objects. They don't seem to be moving relative to each other, with a few exceptions, which we call planets, because they do move relative to the other things, but they're wanderers, planets. So the celestial sphere is, well, it's not an accurate description of what reality. It's an excellent tool for describing where things are located. So it's basically latitude. It's basically like longitude and latitude, but for the sky. Please sign in. So there's a north celestial pole. There's a south celestial pole. These are points. If you continue the actual poles of the Earth, there's a celestial equator, which is an expansion of the Earth's equator. And then there's an important line called the ecliptic. The ecliptic corresponds to the plane of the solar system. So the ecliptic is where you see the sun and all the other planets. It's also where all the zodiac signs are. The zodiac signs are special because they're on the ecliptic. So, if you want to talk about locations in the sky, the point directly over your head is the zenith. You're looking straight up, that's zenith. The horizon is you look out, that's that circle where your vision cuts off, where the celestial sphere meets the Earth. The celestial pole is the projection of the Earth's pole to the celestial sphere. So it's just, if we continue it out from the pole, the actual pole of the Earth that the Earth rotates around, well, there's an apparent pole in the celestial sphere because the Earth is rotating, so the sphere appears to be rotating. The celestial equator is the projection of the Earth's equator onto the celestial sphere. The ecliptic is the apparent path of the sun along the celestial sphere. So it's special because it's where the sun shows up. And then the vernal equinox is one of the two intersections of the ecliptic and the celestial sphere. And it's the one where the sun is moving northwards, and it corresponds to the spring equinox. And that is used as the 0 point for the celestial sphere. It's just a convention. There's two natural points you could choose. You could choose the vernal equinox or the autumnal equinox. And the vernal equinox was chosen, probably because traditionally spring was the start of the year. Now, if you look up at the celestial pole, stars close to the celestial pole never set. They just travel around in circles until the sun comes up and you can't see them around anymore. And if you've heard of the North Star or Polaris, Polaris happens to be a star that is in the same direction as the celestial pole. So it's very close to the celestial pole, so it doesn't appear to rotate. This is a long-term exposure, so that's where these arcs come from. So stars will all revolve in circles around the celestial pole because the Earth is rotating. And stars at greater distances will cross the horizon. Stars close to the celestial pole won't. Who's sun in? And one of the most useful things about this is that if you can locate the celestial pole, like Polaris, you can figure out what your latitude is. You can figure out how far north or south you are on Earth. The pole will be 40 degrees above the horizon for an observer at a latitude of 40 degrees. So it's actually a really simple calculation. You just measure the angle between, the celestial pole, the North Star, and the horizon. It's harder in the southern hemisphere because there isn't a nice convenient star at the celestial pole. If you're at the equator, the celestial pole will be on the horizon. If you're at, say, the North Pole, the celestial pole will be directly overhead. It will be at the zenith. And if you're south of the equator, you can't see the North celestial pole, and vice versa. So that's a very helpful tool for figuring out where you are. It solves latitude. Longitude is harder, just in general. And the celestial sphere appears to move. There are daily motions and annual motions. So the daily motion is the rising and setting of stars. That's caused by the rotation of the Earth. The stars aren't moving. We're spinning around. The stars you can see change as we rotate. The annual motion is caused by the motion of the Earth around the sun, revolution of the Earth around the sun. So the sun will move about 1 degree per day eastward relative to the stars, and will slowly travel through along the ecliptic through the various constellations of the zodiac. So that's where the zodiac signs come through. And planets and other objects near the ecliptic will also travel through these constellations. And the zodiac signs are some of the oldest constellations out there. It turns out they're like, most constellations we talk about, the common names for them are Greek. Many of the zodiac signs are actually Babylonian, even older. Please sign in. Um, Now, there are 7 known objects that move through the stars. And they actually often correspond to the names of the days of the week. The sun, which is tied to the day and the year, that moved against the background of stars. The moon moves against the background of stars throughout the month. And then there's 5 planets that you can see with your naked eye. These are Mercury, Venus, Mars, Jupiter, and Saturn. And planets are called that because they wander. Planet comes from the Greek for wanderer. So they wander among the stars, so they are planets. And one of the things we observe with planets that's very strange, so the sun and the moon move in a consistent pattern against the backdrop of the stars. They're always moving the same direction. It's fairly straightforward. But planets will every once in a while go backwards. It's called retrograde motion. So you'll be looking at the planet, oh, it's the background of stars, and it'll go forward, 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 and then suddenly go backwards for a bit and then forward again. This was one of the things that was super hard to solve as a problem that eventually led to our understanding of, and rejection of the geocentric model with the Earth at the center. Now the constellations, the ancient definition of the constellations is basically, that's a pretty picture in the sky. It's a grouping of bright stars that got named, usually in honor of some mythological figure. And for example, the zodiac constellations are particularly old names. They're actually, most of the constellations are Greek mythological figures. The zodiac constellations are actually older terms that got imported by the Greeks from the Babylonians, for many of them. Now, the modern definition is closer to something like a state. It's just a way to define an area of the sky. Because traditionally, people describe things as parts of constellations, things like that. So now it is just a tool used to talk about places in the sky, because these are existing known things. So it's defined as one of the 88 regions of the sky, each tied to a traditional constellation, and every part of the sky is part of one of these 88 constellations. We just use constellations that already existed to divide the sky into chunks to conveniently talk about things. Because it's awkward to say, this is 30 degrees up and 40 degrees to the left, when you can say it's in Sagittarius. Though those numbers don't correspond to Sagittarius, I just made them up. So there's a whole naming scheme based on the constellations, based on, the brightness of the stars in them. So, the brightest star in the constellation is A, and so on. I believe that's the story. So the celestial sphere is a way we can visualize the sky. The appearance of the sky will depend on the observer's location on Earth. Planets and stars have different motions in the celestial sphere. And the modern definition of a constellation is different from the ancient definition. So let's talk about ancient astronomy. So the ancient science of astronomy was very important to early people. The sky was important to early people because it was an incredibly useful tool for things like using it as a calendar. So it's you can use it as a calendar. So an example of this is that the Nile River used to flood at pretty much the same time every year. And this was incredibly important for the agriculture along the Nile, because the flooding of the Nile needed to be, people needed to prepare for this, and they needed to capture the water from the floods and capture the silt from the floods that made their fields fertile. And it actually corresponds with the rising of the star Sirius, which is an incredibly bright star. It's also been used, the sky is used for navigation. It's used by many people for navigation, though some of the best at it were the Polynesians, who managed to colonize the Pacific Ocean using stellar navigation, which is honestly very impressive. Another example of something tied to the sky, Stonehenge. The various locations in Stonehenge. At certain days of the year, certain things will be through various gaps in Stonehenge. It's aligned to the sky. So, the winter solstice moonrise will be through this gap. The winter solstice moonset will be through this gap, and so on. Because it was used for probably some form of religious purposes. And that was tied to a calendar. Like, Stonehenge was a place where people came to meet up and do stuff. Well, actually, there was another thing down the river where most of the people actually were. But this wasn't a place where people lived most of the time. It was a place for big special events. Now, a lot of our knowledge of astronomy started with the ancient Greeks. So early on, Eudoxus was one of the first people who built an early model of the universe. Aristotle was able to show the Earth was round by looking at the shadow of the Earth on the moon during lunar eclipses, and also proposed the model of a geocentric universe with the Earth in the center and everything else orbiting around it in perfect circles, because he really liked circles. Eratosthenes was able to measure the circumference of the Earth by looking at shadows on a specific day, and he was correct within a few percent, which is honestly pretty impressive. Aristarchus was one of the first people to propose the sun was at the center of the universe. Didn't have any real evidence to back it up, and he also proposed a lot of other much weirder things that didn't make any sense, so he didn't really get much paid attention to. Hipparchus was the Greek to put together the first, one of the first catalogs of the sky. He assembled a catalog of the sky with data from lots of people, was able to measure, was able to, catalog stars that you could see. He created this system to describe them called magnitudes about their brightness, where the brightest stars were first magnitude and the dimmest stars were sixth magnitude. He was also, because he was studying these old records of the sky from previous cultures, he was able to determine that the location of the pole was precessing. It was moving over time, changing over time. And then Ptolemy was able to put together what was the best mathematical model describing the positions of the planets and being able to predict them in a text called the Almagest. This was sort of the astronomy text that went with a related text, which was about astrology, because a lot of early astronomers were all astrologers as well. So for thousands of years, science was dominated by the ideas of Aristotle. And Aristotle put forth this concept that the heavens were perfect. And so everything in the heavens being perfect would need to move in circular orbits at uniform speeds. This led to ages of trouble. And this was the foundation of planetary motion for over a millennium. It's at least, this was almost 2,000 years. I don't remember. Eratosthenes was able to measure the circumference, the size of the Earth, by studying the shadows at various places. He knew that there was a well in a city called Cyrene, which was south down the aisle, and it had no shadow on the first day of summer. So that means at Cyrene, the sun was directly overhead at noon on the first day of summer. So he, in Alexandria, was able to measure the angle of a shadow on the first day at noon on the first day of summer, and found it was about 7 degrees. He specifically found it was a 50th of a circle, but an angle of 7 degrees. And he also was able to get the information about how far apart Alexandria and Cyrene are, from, I assume, people who took the trip regularly. And with this, he was able to determine the circumference of the Earth. Because the basic idea is you assume all the light is coming in the same direction. So if you have an angle of 7 degrees, that means the angle from the center of the Earth between Cyrene and Alexandria is 7 degrees. And if you know the distance between them, and that's, say, a 50th of a circle, the circumference of the Earth is going to be 50 times that. And he was actually accurate to within a few percent. Hipparchus measured magnitudes and precisions. He made a catalog of the sky and divided stars based on their apparent brightness, with the brightest stars in the first magnitude and the dimmest stars in the sixth magnitude. And this system is still, a modified version of this system is still in use today for brightness. It's kind of unfortunate. It means that brighter stars are lower numbers. And when we actually put numbers on it, it means that it goes from like the -20s to the +30s in the range of what we can observe. Because the sun is like -20 something as the brightest thing in the sky. And then the dimmest stuff we can observe with our best telescopes are in, I think, around magnitude 30. Yes.
So as will these slides be on the Brightspace?
They're already up on Brightspace.
Thank you.
All the slides are already up on. He was also able to determine that the Earth wobbles like a top. So the Earth is rotating, but the direction of the axis of the Earth slowly precesses. So yeah, when you spin a top and it wobbles, the top is spinning very fast, but the direction the top is pointing changes over time. That's precession. The Earth does that as well. Much more slowly, but there is a 26,000 year cycle where the pole star changes. So over time, the pole star will eventually move on from being in Polaris to being somewhere else. Eventually, it will be at Vega, for example. But that's in about 14,000 years. So it's about the opposite side of the precession. So here we can see it should, yeah, there. You can see how the pole star will change. And Ptolemy, in this is about the first century AD, was able put together the most detailed model based on a geocentric model that was able to accurately predict the positions of planets for a few centuries in advance. But to do this, he had to build a very complicated structure. Because there's this problem with the planets every once in a while go backwards. And they need an explanation for that. But Aristotle said everything was perfect in the heavens, so everything had to be circles and moving at constant speed. So what Ptolemy did was he added more circles. So what he did, instead of doing the orbit of the object being just around the Earth, he added a circle to his circle. So there's the main orbit or main circle, and then he added what's called an epicycle, which is an orbit of an object around what's called a deferent. This deferent orbits the this is the center of the epicycle that goes around in the circle, a circle on a circle. And then he offset the Earth from the center a little bit with what's called the equant, which is a point opposite the central object. And that was able to get this accurate predictions of where planets would be. Turns out, if you have enough circles on circles, you can make any curve, any pattern you want. So if you keep going with this sort of epicycle structure, you can, in theory, create anything. But because most of the orbits of the planets are actually pretty close to circular, this actually works with only a few epicycles. It's complicated, but doable, but has some issues. But yes, you can predict accurately the location of planets for like a few hundred years. And there's no reason to think, that the Earth wasn't the center of everything, because that's what it seemed like. Then in the Middle Ages, in the West, the fall of Rome led to a decline in Western science. Much of that science and detailed thought continued more in further east. Stuff was in the Eastern Roman Empire, which remained functioning after the Western Roman Empire fell, and also material diffused east into the Arabic and Indian worlds. So working hence through Indian and Arabic astronomers who had gotten access to translated and refined Greek works and developed more advanced mathematics like algebra. And this work ended up returning back to Europe during the Renaissance. So the material sort of diffused out of the Eastern Roman Empire, further east, and then so the study of the sky was important to ancient people for both keeping time and for navigation. Stonehenge and other ancient monuments may have been used for timekeeping or for arranged to be at important, have nice things at important days of the year. The Greek astronomers developed a geocentric model of the universe that lasted for a millennium and was able to make really quite solid predictions. And the Indian and Arab astronomers preserved and improved upon the Greek work. So now let's talk about the difference between astronomy and astrology. So astrology, in the early days, was quite different from what it is today. There were 7 known objects that wandered through the sky. They were tied to the days of the week. The people who were looking at the sky and keeping calendars were often religious figures. So there was always sort of ties to what we were seeing in the sky somehow reflected what was going on Earth or affected us. So people thought this was the case. They had these ideas about how things were affected. So astrological predictions were serious business, and a lot of effort was put into them, which is not the case anymore. So these 7 objects were given special significance. These were the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. And it was thought that maybe they could impact people's lives. Now, the constellations of the zodiac, you may know your zodiac sign. What's special about these constellations, they're not the brightest constellations. It's because they are along the ecliptic. So they're the constellations that the various objects that move across the stars move through. So the sun, the moon, and the planets all move through these constellations. In reality, the Earth's motion changes the position of the sun, and the solar system itself is basically flat. It's a plane. So if you look out along that plane of the Earth's orbit and the constellations you see along there, that's also where you're going to see all the other planets. So the planets are all going to be on roughly the same plane as the sun because the solar system is flat. Now, the idea of natal astrology was that where the sun, the moon, and the planets were at the moment of your birth would help determine your personality and your fortune. This was developed by early Greek astronomers. Ptolemy, who made that famous book, The Almagest on Astronomy, also wrote treatises on astrology. Basically, every astronomer was also an astrologer until relatively recently. Please sign in. Please. Good. Yeah, go ahead. And this ancient Greek model is still the basis of astrology today, though much weakened. So your horoscope that you can see is very simplified. They divide the sky into 12 sections. These are the zodiac constellations you're familiar with. The sun spends about a month in each constellation. But we just talked about the fact that the Earth is precessing. This actually changes the location of the sun and the stars and such relative to the constellations. It slowly changes the position. So we're actually about a zodiac sign off from what your zodiac charts would say. Because people just wrote down some dates and they just kept using them. Even though it's so, for example, on May 6th, the sun was in Aries. But if you look up what May 6th corresponds to as your sign, it would be a Taurus. So modern horoscopes are, the trick is you write something vague enough that it can apply to anybody. The same trick as writing a fortune cookie fortune. So newspaper internet horoscopes often just look at the sun sky. That means about 8% of the population has the same horoscope prediction. A complete horoscope, people still do this, uses not only the sun, but the moon and each of the 5 planets. There is some rules in theory about interpretation. And these interpretations vary from astrologer to astrologer, and a lot of the time what's going on is they're going to tell you what you want to hear. Even if they don't mean to, they're likely to be telling you what you want to hear. Now, from the Greeks to the Renaissance, astrology and astronomy were very similar. So famous astronomers you may have heard of, who we're going to talk about in a bit, Tycho, Kepler, and Galileo, they were all also astrologers. But by the 1700s, the two separated. Astronomy was the study of the sky, while astrology was the study of the sky's perceived impact on our lives here on Earth. Because in the 1700s, that's where the Enlightenment and more modern scientific concepts started to come out. So a lot of weird stuff was still going on before that. So like Isaac Newton, for example, was also an alchemist. Like he wrote books on alchemy.
This looks all.
It's sort of the precursor to chemistry, but it had a lot more mystical stuff in it as well. I don't think he was an astrologer. So astrology is like a pseudoscience. It's a subject that purports to be scientific, uses a lot of scientific terminology, but it's not based on rigorous testing like a true science. So pseudoscience is the trick for the pseudosciences use, they sound like science, they use sciencey words, but they don't have anything being really tested. There's no doubt there.
There's no scientific way to prove it. Right?
Yeah, or more accurately, the trick for science is everything needs to be disprovable. You need to be you need to set up experiments that could show you are wrong. And pseudoscientists will never do that. And statistical studies have shown no relation between one's horoscope and their lives, and horoscopes are vague enough that you can always find some truth in them. That's the trick of it. It's similar to a fortune. So astrology is the study of the position of the sun and moon and the planets and how their perceived impact on our lives. There were a lot of like ideas, philosophical ideas that they were affecting how things functioned on Earth. But to our modern understanding, they have little to no effect on day-to-day stuff on Earth. I mean, the gravitational pull is minute. You probably have a stronger gravitational pull from like other people in this room than other planets. Astronomy is the study of celestial objects. Astrology and astronomy were the same in the distant past, and there's no scientific basis or truth to astrology that's been shown by statistical studies. So let's talk about the point where modern astronomy, well, not modern astronomy, but where astronomy started to change. When we got rid of the geocentric model, this is known as the Copernican revolution. So the sun, the moon, and the stars all have relatively simple movements in the sky, consistent with an Earth-centered system. So if you look at the sun, the moon, and the stars, everything makes sense for stuff traveling around the Earth. But the planets were a problem because they move with respect to the fixed stars. They change in brightness. They change their speed. They sometimes go backwards. They have retrograde motion, where instead of traveling normally they would travel east, but every once in a while for a short period they'll travel west. And they're difficult to describe in an Earth-centered system. You can do it, but you have to do messy things. So you can explain this by basically you put the planet, you rotate the planet around a point, and then rotate the point around the Earth. And as the planet rotates around this epicycle, sometimes it'll go backwards. But this was used to explain planetary motions and the fact that things were moving in and out and stuff like that. Now, when you start to accurately track planetary motion, you needed lots of epicycles. Yes. Yeah. So here is Ptolemy's model, and you can see it's lots of epicycles. Every planet has an epicycle. There were some extra ones in there. This is very complex. It worked, but it was very complicated. So the big change was that if the Earth was not the center of the solar system, but all the planets orbited around the sun instead, then it would be a lot easier to explain this retrograde motion. The sun at the center was suggested by Aristarchus, but it wasn't seriously considered. He had no real evidence for it. And then Nicholas Copernicus put forth an actual detailed model of, he lived from about 1473 to 1543. He was a Catholic monk. He suggested the Earth was a planet, and that all the planets, including the Earth, orbited the sun. This was in some ways a simpler model. It explained retrograde motion. Unfortunately, to get accurate calculations, he was not able to eliminate epicycles. As it turns out, the orbits of the planets aren't perfect circles. I didn't know this was still using perfect circles, so it was not able to actually eliminate epicycles. In fact, it ended up with almost as many as Ptolemy had. And he published this in a very dry book in 1543, like right before he died. He made the excellent decision to die before this happened, so as to not get in trouble with die right around when he published the book, so as not to get in trouble with the church. Because the idea of a heliocentric universe, there were scriptural reasons that the Catholic Church liked this Aristotelian geocentric model. There were theological reasons that they liked it. And a lot of this stuff happened during the Protestant Reformation. So everybody was on edge about religion. So the heliocentric model put the sun at the center of the universe. The Earth and the planets revolved around the sun. One of the big things that it predicted that no one saw was parallax of stars. If the Earth is traveling around the sun, when the Earth is on one side of the sun, as opposed to when the Earth is on the other side of the sun, you'd see slightly different positions of the stars against the background of the Earth. Like if you hold your finger out and close one eye and switch to the other, it looks like your finger moves. That's parallax. The heliocentric model predicts parallax of stars, which hadn't been seen. So that was a problem with it. But it did simply explain retrograde motion, and however was not able to eliminate epicycles fully. So parallax is the apparent motion of a nearby object. This was predicted by the heliocentric model. And one of the biggest arguments against it for the longest time was that no parallax had been seen. Because parallax of stars was not detected until 1838. And that's because stars are a lot further away than people thought. And the size of parallax corresponds to how far away things are. The further away something is, the smaller the parallax. And stars are a really long way away. So the nearest star to us has a parallax of between January and July, between opposite sides of the Earth orbit, has a parallax of less than 1 arc second. So that's less than 1/60th of a 60th of a degree across the sky. Which is why it wasn't discovered until 1938, because you can't actually see parallax without telescopes. But it does explain retrograde motion very well. So this is the apparent backwards motion of planets. For a geocentric model, you have to explain it with epicycles, as you can see on the right here. But in a heliocentric model, it's just like when you pass another car on the road, it appears to be going backwards from your point of view. That's retrograde motion. It's when the Earth is traveling faster than the other planet around the sun. It's passing it up. The heliocentric model was not immediately accepted. It predicted parallax, no one had seen it. So Tycho Brahe never liked the heliocentric model, for example, and he was the guy with the best astronomical data in the world at the time. This was a bit later, but he rejected because he never saw parallax. And there was no sign that the Earth was moving. When you're on the Earth, it doesn't feel like the Earth is moving. And lastly, because Copernicus stuck with circles, it wasn't any more accurate than the geocentric model. It was more realistic, but it still required epicycles to count for motion, just not for retrograde motion, because they continued the use of circular orbits. And it took them a long time to get rid of that. So a heliocentric model of the solar system, it easily describes the observed motions of the planet without excess complications. The issue is the details. Now, one of the big supporters of this heliocentric model was Galileo Galilei. He lived from 1564 to 1642. He did experiments to study the motion of objects. He came up with the concept of inertia, the idea that objects remain in motion unless some force acts on them. And he discovered that all objects accelerate at the same rate due to gravity. He also was the first person to use the telescope to observe the sky and record and publish his observations. Probably wasn't he didn't invent the telescope. He heard about it, was able to make his own. The telescope was invented by Dutch lens grinders, who were doing things like making glasses and stuff. But he was the first person to observe the sky with a telescope and publish. Probably wasn't the first person to observe the sky with a telescope because, honestly, who does look up? But he was the first person to actually publish his observations. And he saw a bunch of stuff that started to poke holes in the geocentric model. He looked at a whole bunch of different things that you could do yourself with a telescope, except for the first one. Don't do that one. He looked at the sun and observed that the sun had spots, so it wasn't a perfect spherical object, and that it rotated. So don't do that. Do not look at the sun. It's very bad for your eyes. Definitely don't look at the sun through a light collection, amplification, and collection device, i.e. a telescope. There are sun telescopes. They observe the sun indirectly. You project the sun on a wall, basically. He looked at the moon. He observed the moon had mountains and craters, so it wasn't perfect. This was poking holes in this idea that the heavens were this perfect celestial sphere. He observed that Venus had a complete cycle of phases. So this is not what you'd see in a geocentric model of the universe. You'd only get half the phases. You wouldn't get the complete cycle that he observed. So the phases he saw of Venus matched up perfectly with a heliocentric model, where the Venus was orbiting the sun. He observed that Jupiter had 4 satellites orbiting it, which allowed things to orbit something other than the Earth. He saw that Saturn had 2 lobes. He couldn't actually resolve the rings yet, but what he was seeing was the rings. Again, not perfect. And he was able to see that the Milky Way, which looks like sort of a bright streak across the sky, was actually made of countless stars. There's lots and lots of stars out there. There wasn't some small finite number of stars. So here are some of the telescopic observations of Galileo. So this is, a sketch of the moon showing the surface with craters and mountains. These are the phases of Venus, and that the way this Venus changes size as it goes through its phases is also relevant here, because that corresponds with what you'd see in an actual, if Venus was orbiting the sun, where when it is full, it is smaller and further away. And then here is an observation of the moons of Jupiter orbiting. And thus, the 4 moons that Galileo saw are referred to as the Galilean moons of Jupiter. Now, Galileo published his observations in 1610, and then he went on to present his ideas in about the most acerbic and aggressive and kind of insulting way to his critics, which is a big part. So in 1660, the Inquisition banned books supporting the heliocentric theory as heretical. So a big part of this is that in 1616, this was the 30-year, the Protestant Reformation was in high swing. The 30 Years' War had just started. There was a massive war across Europe going on, having to do with fights over religion. The Catholic Church was in, they were being reactionary and trying to do everything they can to batten down the hatches. So they were being super critical. So if the Protestant Reformation wasn't going on, he probably could have gotten away with this. And then in 1632, he published his book, Dialogue Concerning the Two Chief World Systems. Now, the thing is, he was asked to present both sides in an equitable manner, and then he wouldn't put the words of the Pope in the mouth of a character named Simplicio. He basically called the Pope a simpleton. And yeah, that got him investigated by the Inquisition, tried for heresy, found guilty of heresy for holding, teaching, and defending the heliocentric view, and placed under house arrest until his death in 1642. Galileo's big problem was he was kind of a jerk. like if he wasn't so aggressive, he probably could have gotten a much better situation. The timing wasn't great either. And Galileo's book and Copernicus's book were removed from the Index of Banned Books in 1820. And in 1992, Galileo was formally cleared by the church. His ideas were accepted well before both of those dates. Well, I mean, when it was removed, at that point, it was fully accepted. But the bureaucracy of the church moves slow. By 1992, I think the Vatican is building modern telescopes. So what happened? Galileo couldn't prove the heliocentric theory. He also didn't like and wouldn't talk with the guy who would. So the proof wouldn't come until long after his death. And the Reformation was in progress. The church was losing power. And so lots of internal politics were important here. And Galileo's personality was horribly abrasive. So the book portrayed defenders of the geocentric theory as simpletons. They put all the geocentric ideas in the mouth of a character named Simplicio. I mean, it's pretty out there. So Galileo observed these things, that the moon had mountains, valleys, and craters, the sun had imperfections that it rotates, Jupiter had moons, and Venus has phases. These were all contradictions to the general belief that the heavens were consistent and immutable, but he didn't have any way of making a model that could predict the location of planets. Or an explanation for how this worked. So the phases of Venus, for example, are impossible to explain in the Earth-centered model of the solar system. Because in an Earth-centered model, you never see a full Venus. You'd always see partially illuminated Venus. So Venus would have to be orbiting the sun. And Copernicus proposed this heliocentric model of the universe. The Earth moved around the sun in a circular orbit. This model easily explained retrograde motion, but required parallax. Galileo made and published the first telescopic observations of astronomical objects, and he found circumstantial evidence for the heliocentric model, but couldn't prove it. And he was tried and convicted by the Inquisition because he went about presenting his evidence very abrasively. Now, the actual model wasn't put together until a little later by Kepler. It was about the same time. There were a lot of the same time. So the universe, the early ideas of this, the universe is geocentric. This is the intuitive idea. There's no measurement of parallax of stars. The Earth doesn't seem to move. Copernicus suggested a heliocentric universe, suggested the Earth was a planet. This is not an obvious thing, and it doesn't really correspond to what we see when we just look out at the sky. And he had difficulties in explaining the orbits using circular orbits, and couldn't eliminate episodes. Now, Tycho Brahe lived from 1546 to 1601, so he actually died before Galileo, was the last great pre-telescopic observer. He was also a character. He got his nose cut off in a duel when he was young, and he had a silver nose for special occasions. But he got banned from several countries. If you haven't signed in, please do. And he made the most accurate observations of the sky at the time. And this was decades worth of data. Now, he didn't really communicate much with Galileo because he was Protestant, Galileo was Catholic. And again, this was the middle of the Protestant Reformation. And he found that his observations didn't fit with the geocentric model. But he didn't like the heliocentric model because he couldn't observe parallels. So he proposed his own bizarre hybrid model, where the sun orbited the Earth and the other planets orbited the sun. Which is this wacky model where Mercury and Venus orbited the sun. All the other planets orbited the sun, and the sun orbited the Earth. The Earth is this was to deal with the lack of parallax. This is the sun and the moon orbit the Earth, and all the other planets orbit the sun. It's sort of this crazy model. Now, Johannes Kepler lived from 1571 to 1630. And he was actually the guy who was able to explain planetary motion by putting together a model. He worked as Tycho's assistant, and when Tycho died, he absconded with a whole bunch of Tycho's data. And honestly, he basically stole it. Because Tycho was super secretive about it. And then he spent years trying to do math about it, because he had a number of weird ideas about how he thought the solar system should work. He liked heliocentrism, but he had this idea about nested platonic solids describing the orbits of the various planets. But eventually, he got to this point where he did a whole bunch of really kind of complex math to get to the point where he was able to start making predictions, modeling where he worked on Mars. And eventually he got to this point where there was only so good circles could get. And he went, there's 8 minutes of arc that I cannot resolve. I'm going to throw this out. I'm going to throw out circles, and I'm going to throw out uniform motion. It took him a while and a whole bunch of weird attempts. But he eventually got back to this thing where, like, simple circles just didn't work. There was a small error that he could not get rid of. And so he abandoned circles. And he went with ellipses. And he went with ellipses in the most circuitous, kind of got there through an incredibly circuitous route. He like started with ellipses, rejected them because he made a mistake, and then eventually got back to them through some very weird construction. So Johannes Kepler was able to describe the motions of the planets and make excellent predictions of their positions through what we call his 3 laws of planetary motion. So the orbits of the planets are ellipses. So ellipses are kind of like a stretched circle. And they have 2 special points called focuses in them. On an ellipse, if you choose any point on an ellipse, if you add up the distance to the 2 focuses, it'll be the same number. That's sort of how an ellipse is defined. One of the ways. So an ellipse has a center, a focus, and a major and a minor axis. The major axis is the long axis, the minor axis is the short axis. And the eccentricity of an ellipse is a measure of basically how squashed an ellipse is. If the eccentricity of an ellipse is 0, it's a circle. If the eccentricity is 0.999999, it's very flat. At 1, it's a line. So that's sort of a measure of how squashed the ellipse is. So Kepler's law says all the orbits of the planets, you put the sun in one focus of the ellipse, the planet orbits around the ellipse. So no longer circular orbits, no longer the sun in the center. Exactly. It's at one of the focuses of the ellipse. And the other thing he did was that we're also saying, nope, these things don't go around the sun at a constant speed. They change speed throughout their orbit. And he was able to work out what that speed would have to be. So if you draw a line joining the sun and the planet, it will sweep out equal areas in equal intervals of time. What that means is when the planet is close to the sun, it goes faster. When it's further from the sun, it goes slower. So the planet will change speed as it orbits. So it moves faster when it's close to the sun at perihelion, and moves slower when it's further from the sun at aphelion. Perihelion is the closest to the sun, aphelion is the furthest. So an imaginary line connecting the sun and the planet will sweep out equal areas in equal time. And these are fairly exaggerated ellipses. So the actual planetary orbits are much closer to circular. But they're like this so you can see. Now Kepler's 3rd law of motion. So Kepler's first 2 laws of motion describe how the planets, how an individual planet orbits the sun. Kepler's 3rd law of motion relates the orbits of the planets to each other. It's called the harmonic law sometimes. But what it is that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. So if you measure the period in years and the semi-major axis, that's just the average distance from the sun. It's half the major axis. So if you take the long distance across the orbit, cut it in half, that gives you the average distance to the sun. And that in astronomical units, period squared will equal semi-major axis cubed. So here, for example, we have the period in astronomical, the mean radius in astronomical units. This is the semi-major axis for all the planets and Pluto. And here we have the period in years. And here we have r squared over t cubed. And you can see they're all basically one. Just
Why is the one for first, like, for the last one, why is it that from 0, 0, 0, 1? For a base rate.
It's because they're just showing it to two decimal places. Because it's 1/1, which is 1, you can write that as 1.00. They're just being consistent. Notice how all of these numbers are two decimal places. So all of these are just two decimal places. But yes, it is exactly. So the square of the period of a planet's orbital motion is proportional to the cube of the Minnesota axis. This is another chart showing. And Kepler's laws of motion are important because they overturned more than a millennium of focus on circular orbits and uniform motion, and they were better at predicting the positions of the planets than any previous model. Now, there wasn't a physical basis to describe why these things happen. But Sir Isaac Newton, quite a bit later, was able to derive Kepler's laws from his law of gravitation. And that will make them more general. As they stand, they only apply to objects orbiting the sun. The way Kepler wrote them, they only apply to objects orbiting the sun. But when Newton was able to derive Kepler's laws, he was able to make a more advanced version of them that would apply to any objects orbiting in space. And we actually use that to this day to measure the mass of stars. So we'll talk about that later. But so Isaac Newton was able to take Kepler's laws and his laws of motion and his universal gravitation and combine them to derive, take his laws of motion and universal gravitation and derive Kepler's laws from them. So generate Kepler's laws from whole cloth, which means he had an explanation for why they happened, how, what led to them. He had a mechanism. So Tycho Brahe made decades of careful observations of the planets. Tycho's observation allowed Johannes Kepler to come up with his 3 laws of planetary motion. And these laws were empirical and based on observation, and the physical understanding would have to wait for Sir Isaac Newton. And so when we deal with the laws of planetary motion, so the distance from the Earth to the sun is called an astronomical unit. Its actual length can be measured by bouncing a radar signal off Venus and measuring the signal's travel time. For the longest time, we knew all the relative distances of all the planets, but we didn't have a good absolute distance. So we knew the distances of all the planets in terms of astronomical units, because you could work that out through geometry. But it would be the same geometry whether an astronomical unit was 150 million kilometers or only 100 million kilometers or something. It was very tricky to actually get a reference for a real distance. It happened surprisingly late. And it turns out pretty much all of our distance scales in space are built off of that concept. We build up like a ladder. So Newton was able to put together this model of gravity that actually was able to explain Kepler's laws. So some of the early ideas, Galileo, in his studies of motion, came up with the concept of inertia, that objects would remain in motion unless acted on by some force, and that all objects follow the same rate in a gravitational field. This was excellently demonstrated by the Apollo 15 crew on the moon, who replicated Galileo's experiment on the moon, which conveniently has significantly less gravity, so it is much easier to do this experiment. And it also has no air, so that doesn't interfere. So the reason that if you drop two random objects, they don't fall at the same rate is because of air resistance. So if you get rid of air, they will. But it's also
Jim,
hard
we
to tell.
copy to both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Superb.
So when we talk about motion, we need to talk about velocity and acceleration. These are vector quantities. Velocity is how fast you're moving in what direction. Acceleration is how velocity is changing. So acceleration occurs when velocity changes, when you speed up, when you slow down, but also when you change direction. If you're in a car, whenever you feel pulled around in a car, when you speed up, you feel pulled backwards in the opposite direction to the acceleration. When you slow down, you feel pulled forwards. And when you turn, you feel pulled out to the edge of the curve. Now, Sir Isaac Newton, who lived from 1643 to 1727, developed calculus to solve problems of motion. So while it's possible to do these calculations about planetary motion without calculus, it is much easier with it. And he gave us the three laws of motion, and he also discovered the universal law of gravitation. So Newton's laws of motion explain how objects interact with the world and with each other. Newton's first law is that an object at rest will remain at rest, and an object moving in a straight line at a constant speed won't change its motion unless some external force acts on it. Newton's second law is that when a force is exerted on an object, its acceleration is inversely proportional to its mass. So the more force, the more acceleration, the more mass, the less acceleration. And Newton's third law is when an object exerts a force, object A exerts a force on object B exerts an equal and opposite force on object A. If you push on something, it pushes back on you with equal and opposite force. And the law of universal gravitation is that any two objects that exist are attracted to each other by a force that's proportional to the product of their masses multiplied together, and inversely proportional to the square of their distance. So the more massive they are, the bigger the force. The further apart they are, the less the force. And this is universal. It applies to any two objects in the universe with mass. And it's always attractive. It's never repulsive. It always pulls things together. Now, in our everyday life, we don't notice the gravitational attraction between random objects because it's actually very weak. But the Earth is really, really big. And so we're attracted towards the center of the Earth because the mass of the Earth is a really big number. So on the Earth's surface, the acceleration due to gravity is approximately constant and directed towards the center of the Earth. Because the force is proportional to the mass, because of gravity, that means the acceleration ends up constant, because the more mass you have, the more force you have, and they cancel out. Question?
Yeah. Did what did people think of gravity like before like moving? Because
So people thought there was sort of a natural place that things wanted to be.
the Earth is they thought the Earth was sphere, so
Well, yes, so heavy things wanted to be in the center. And lighter things wanted to be like above. So it was like there was certain things had a natural sort of motion. The ideas of motion were very different. Everything was propelled in some sort of concept. So the idea was that things would travel to where their natural place was, and for a lot of things there was ground in the way. So the gravitational pull of the sun keeps the planets moving in their orbits. So basically, to keep it in orbit, the trick is to move sideways fast enough that as you fall, you miss the ground. So basically, a planet orbiting the sun is constantly being pulled towards the sun, but it's moving sideways such that it just ends up constantly missing the sun and traveling around and around. So, and massive objects will actually orbit around the common center of mass. So if you have two equally massive objects orbiting each other, the point they'll orbit is the point exactly in between them. In the solar system, this is also true. The massive objects in the solar system all orbit their common center of mass. It's just the sun consists of 99.9% of the mass in the solar system. So the common center of mass of any two objects in the sun and any other object in the solar system is inside the sun. So if you have equal masses, the center of mass is in the middle, but if you have much more mass, the center of mass is closer to the more massive object. It's like the point where you balance them on a balance beam. And we find that Kepler's laws are a consequence of Newton's laws. The point that the two will orbit is actually common focus. They both travel in ellipses. And because of this, it's actually possible by observing the orbits of objects that are orbiting each other to work out their masses. Which is incredibly helpful. So Newton revised Kepler's third law. So Kepler gave us p squared equals a cubed. Newton revised this to give p squared equals mass 1 plus mass 2 equals a cubed. And if we can observe, so these are the masses of the objects in solar masses, if we're going to use years and astronomical units. This allows us to measure the mass of an object from the parameters of the orbit. So if you have two things orbiting each other, if you can get its period and its semi-major axis, you can figure out the mass of the two objects. And if you can look at the relative orbits of the two objects, you can actually work out their relative masses. Because you can figure out how far they are from the center of mass and which one's the heavier one and which one's the lighter one. So that's actually how we measure the mass of stars. It's one of the primary ways to do so. So all objects will fall at the same rate in the gravitational field, regardless of mass. Newton gave us 3 laws of motion, and Newton gave us the law of gravitation. Sorry for running a little over, but that will be all for today. So stop sharing.